Welcome to CognitionChunks. Unfortunately, I could not find videos that match the type of fractal being discussed in some cases, so follow the text rather than the visuals when they do not match. Future episodes of this series will use generated images to try to match more accurately. For centuries, mathematics relied heavily on smooth Euclidean shapes. Circles, squares, spheres. These were the building blocks of our understanding. Yet the natural world rarely adheres to such perfect forms. Look around, and you'll see a different kind of geometry at play. Clouds are not perfect spheres. Mountains are not cones. Lightning doesn't travel in a straight line. Nature is full of intricate patterns and irregular shapes that defy easy description. These shapes, with their rough edges and intricate details, hint at a deeper, more complex geometry. Fractal geometry, as a distinct field of study, emerged relatively recently. It challenged the traditional Euclidean framework, offering a new perspective on dimension and shape. Fractals go beyond the familiar 1, 2, or 3 dimensions of our everyday experience. They exist in the realm of fractional dimensions, a concept that once seemed paradoxical but is now essential to understanding their intricate nature. A fractal's dimension is a measure of its complexity, reflecting how much space it occupies between integer dimensions. Our journey into the realm of fractals begins with a seemingly simple, yet profoundly impactful, mathematical construct, the Cantor set. Conceived by German mathematician Georg Cantor in the late 19th century, this set challenged conventional notions of infinity and laid the groundwork for understanding the intricate nature of fractals. Imagine a straight line segment. Now, divide it into 3 equal parts and remove the middle segment. You're left with 2 smaller segments. Repeat this process, dividing each remaining segment into thirds and removing the middle portion infinitely. What remains is the enigmatic Cantor set. Around the same time that Cantor was exploring the depths of infinity, Italian mathematician Giuseppe Peano introduced another groundbreaking concept, the space-filling curve, now famously known as the Peano curve. This intricate construction challenged traditional notions of dimension and paved the way for understanding the complex relationship between fractals and the spaces they inhabit. Imagine a curve, a continuous line, that is meticulously drawn to pass through every single point within a square. This is the essence of the Peano curve, a one-dimensional entity capable of completely filling a two-dimensional space. Its existence raised profound questions about the nature of dimension and continuity. In the early 20th century, Swedish mathematician Helge von Koch introduced a curve that would become a cornerstone of fractal geometry, the von Koch curve. This seemingly simple construction, often referred to as the snowflake curve due to its intricate snowflake-like appearance, brought to light the perplexing nature of measuring irregular shapes and further solidified the concept of fractional dimensions. Now imagine a straight line segment, divide it into 3 equal parts, and replace the middle part with 2 sides of an equilateral triangle, forming a tent-like shape. Repeat this process for each of the resulting segments infinitely. This iterative construction gives rise to the infinitely detailed von Koch curve. Around the same time that von Koch was exploring the paradoxical nature of coastlines, Polish mathematician Wacław Sierpiński introduced another iconic fractal, the Sierpiński triangle. This visually striking shape, formed through a simple yet elegant iterative process, unveiled profound connections between geometry, topology, and the concept of self-similarity at different scales. Begin with an equilateral triangle. Connect the midpoints of each side, forming 4 smaller congruent triangles. Remove the central triangle, leaving 3 triangles behind. Repeat this process, connecting midpoints and removing the central triangle, infinitely for each remaining triangle. Our exploration of fractals takes us deeper into the realm of complex numbers and iterative functions with the captivating Julia sets. These intricate shapes, named after French mathematician Gaston Julia, emerge from the repeated application of simple rules to complex numbers, revealing hidden patterns and unexpected beauty within the seemingly abstract world of complex analysis. Imagine the complex plane, a two-dimensional grid where each point represents a complex number. Now, consider a simple iterative function, a rule that takes a complex number as input and produces a new complex number as output. Applying this function repeatedly, starting with different initial points on the complex plane, leads to a fascinating divergence of behaviors. Section 2. The Infinite Atlas, exploring the Mandelbrot set. Building upon the foundation laid by Julius Sets, we arrive at one of the most iconic and recognizable fractals of all, the Mandelbrot set. This mesmerizing shape, named after the pioneering mathematician Benoit B. Mandelbrot, emerged from the study of a seemingly simple iterative function, yet it revealed a universe of infinite complexity and self-similarity. Consider the iterative function z2 plus c, where z is a complex number and c is a constant. For each point c in the complex plane, we apply this function repeatedly, starting with z equals 0. As with Julius sets, some points c lead to bounded iterations, while others result in values escaping to infinity. Section 1. The Fractal Geometry of Nature. The year 1982 marked a watershed moment in the history of fractal geometry with the publication of The Fractal Geometry of Nature by Benoit B. Mandelbrot. This seminal work, both a scientific treatise and a visual masterpiece, brought fractals to the forefront of scientific and popular discourse, forever changing the way we perceive the world around us. Mandelbrot, through his extensive research and captivating writing, argued that the traditional Euclidean geometry, with its emphasis on smooth curves and perfect shapes, was inadequate for describing the complexity and irregularity inherent in nature. He proposed fractal geometry as a new language, a powerful tool for understanding and analyzing the rough, fragmented, and seemingly chaotic forms found throughout the natural world. Section 2. Measuring the irregular, the box counting dimension. With the formalization of fractal geometry came the need for rigorous tools and techniques to characterize and measure these intricate shapes. One such tool, the box counting dimension, provided a practical method for estimating the fractal dimension of real-world objects and images, enabling a quantitative analysis of their complexity. Imagine overlaying a grid of squares like a fine mesh onto an image of a fractal. As the size of the squares decreases, we count how many squares are needed to cover the fractal. This process is repeated for different grid sizes, and the relationship between the number of squares and their size provides a measure of the fractal's dimension. Beyond the third dimension, unveiling the Menger sponge. As our journey through the fractal landscape continues, we find ourselves venturing beyond the familiar three dimensions, pushing the boundaries of our spatial intuition. Here, in the realm of higher dimensional geometry, we encounter the mesmerizing Menger sponge, a fractal object that stretches our imagination while revealing the elegance of fractal concepts in higher dimensions. Imagine a cube, a solid three-dimensional object. Now divide each face of the cube into 9 equal squares, like a tic-tac-toe board. Remove the central square on each face and the cube at the very center, leaving behind a structure with 20 smaller cubes. Repeat this process for each remaining smaller cube, infinitely. The resulting intricate and porous structure is the Menger sponge. The spectrum of complexity, delving into multifractals. Our exploration of fractals has, until now, focused primarily on shapes exhibiting a uniform type of self-similarity. However, the world around us often presents a more nuanced and complex picture, where different parts of a system may exhibit varying degrees of irregularity and scaling behavior. This is where the concept of multifractals comes into play. Unlike simple fractals, which are characterized by a single fractal dimension, multifractals possess a spectrum of dimensions, reflecting the varying levels of complexity within a single object or phenomenon. Imagine a coastline where some sections are relatively smooth, while others are incredibly jagged and intricate. A multifractal approach allows us to capture this range of scaling behavior. Section 1. Fractals in the digital age, the power of compression. With the advent of the digital age, fractals transcended the realm of pure mathematics and found a new stage in the world of computer science. One groundbreaking application emerged in the late 1980s with the development of fractal image compression, a technique that harnessed the power of self-similarity to represent complex images with remarkable efficiency. Pioneered by mathematician Michael Barnsley, fractal image compression relied on the observation that many natural images, with their inherent fractal-like qualities, could be approximated by iterating simple geometric transformations. Instead of storing the entire image pixel by pixel, this innovative approach stored only the mathematical rules for generating the fractal patterns, resulting in significantly smaller file sizes. Section 2. Nature's Code. Fractals in Science and Beyond. Beyond their impact on computer science, fractals permeated a wide range of scientific disciplines, offering a new lens through which to view and understand the natural world. From the intricate structures of living organisms to the vast patterns of the cosmos, scientists began to recognize the pervasive influence of fractals in shaping the universe around us. In biology, fractals provided a framework for understanding the branching patterns of trees, the intricate network of blood vessels, and the convoluted folds of the human brain. Geologists used fractals to model the formation of mountains, the erosion of coastlines, and the distribution of earthquakes. Physicists found applications in describing turbulent flows, the behavior of chaotic systems, and the structure of the universe itself. Section 1. The Enduring Legacy of Fractals. Our journey through the realm of fractal geometry has taken us from the abstract world of mathematical sets to the intricate patterns found in nature, art, and technology. We have witnessed how a few simple rules repeated endlessly can give rise to infinite complexity and breathtaking beauty. We have seen how fractals, once considered mathematical curiosities, have become essential tools for understanding the world around us. The legacy of fractal geometry extends far beyond the confines of academia. It has permeated popular culture, inspiring artists, musicians, and filmmakers. Fractal designs adorn everything from clothing and jewelry to architecture and computer graphics. The Mandelbrot set, with its iconic shape and infinite detail, has become a symbol of the beauty and wonder of mathematics. Section 2. Uncharted Territories, Fractals in the Future. While we have explored many facets of fractal geometry, our journey is far from over. The field is constantly evolving, with new discoveries and applications emerging all the time. As we venture further into the 21st century, several exciting frontiers beckon, promising to push the boundaries of our understanding even further. One such frontier lies in the realm of quantum mechanics, where researchers are exploring the possibility of quantum fractals. These strange and exotic objects exist in the realm of the very small, where the laws of classical physics break down. Understanding quantum fractals could lead to breakthroughs in quantum computing, materials science, and our understanding of the fundamental nature of reality itself. Thank you for joining us for another Cognition Chunks. Future episodes of this series will try to explain the mathematical developments between fractal discoveries according to GPT. Please like and subscribe.